Hi, my name is Dustin Yanofsky. We're going through every single section of this book, Monoidal Categories, Unifying Concepts in Mathematics, Physics, and Computing by MIT Press. We're up to chapter 5, where we actually start talking about monoidal categories, and we're going to do section 5.1, strict monoidal categories. So let's recap. So chapter 1 through 4 is basically an introduction to categories, but along the way, we saw that many times you can take two elements of a category and bring them together and make a third element of the category. Okay, so that's an operation on the categories. So let's just go through some examples where we saw this. In the category of set, okay, we saw that you could take a set S, you could take a set T, and you could take the product of them. Okay, you could also take a set S, and you could take a set T, and you could take the co-product of them. I think we wrote it like that. Okay, but not only does it work for the objects, it also works for the morphisms. So you could take a morphism and another morphism in the category, and you could take the product. You could take one morphism, and maybe we did this with a plus, and another morphism, and we could talk about with the co-product. So that's an example of a category where you take two things in the category, or take two things in the category, and you bring it together and do that. That's an example of a monoidal category. We also saw it in groups, in the category of groups, where you have a group G and a group G prime, and you can take the product of them, okay, as well as group homomorphisms. We saw it with partial orders. Partial orders, you can take up one partial order, and you take another partial order, you can take the product of them, you can take the co-product of them. We also saw it in the category of categories. You take one category, you take another category, and you can take the product of them. Okay, hold on. Okay, now, with all these examples, and we're going to see a lot more today, with all these examples, you can also talk about what these combining operations, what rules they satisfy. So in order to do this, let's go back and think about regular numbers. Okay, so you have a regular number. Okay, X, Y, and Z. And you have some operation. I don't know what the operation is. We're going to just do it like this. So now we can ask, hello, is this equal to X? Whatever this operation is, if we have three of them, is that equal? If they are, we call it associative. Okay, so with numbers, plus and times is associative, so we say yes. Subtraction and division is not associative. Okay, another thing we can ask is, here, is this equal to this? Okay. Okay, when you change the order, is it, if it is, we call it commutative. We call that operation where it is, where this holds to be commutative. And again, plus and times is commutative, minus and division is not commutative. Okay, so that's about numbers. Well, every time we combine things with a category, we're also going to ask questions about this. To what extent is it associative? To what extent is commutative? Okay, but we're going to see that there's a much richer theory. There are many more things you can do in categories than just numbers. By numbers, we can say yes or no, they are equal or not. With categories, we're going to have a lot more things that could happen. Okay, so great. So this is monoidal categories. We're going to talk about combining them, and we're going to talk about what could happen when you combine them, when you combine objects in this category, in such a category, and what's the possibilities of what can happen. And we're going to go through section 5.1, 5.2, and 5.3. Those are three sections that show you how they're doing it. We start off with the strictest type of thing, the stuff that works the best, that's section 5.1, and then we go into more general, and then more general than that, and we talk about that. Okay, so let's do this. Section 5.1, it's called strict monoidal categories. Let me just tell you what it is. It's a category, so this is a definition. It's a category, okay, and what we're going to be able to do is take an operation on these categories. So the operation is usually written like this. We're going to call that tensor, and what it does is it takes two elements of the category and brings it to one element of the category. So this is the core of the idea. Take two elements and give you out an element by doing those operations, okay? Furthermore, we have an object I, which is a member of the category, okay? But we require, to be a strict monoidal category, we require the following things: that A tensor B tensor C, these are three elements in this category, is equal to A tensor B tensor C, like that. Okay, so we assume it's strictly associative, and furthermore, we have the following: A tensor I is to be thought of as the unit of the category, is equal to A, which is equal to, so in other words, the I doesn't do anything. It's like the 0 of the plus operation or the 1 of the multiplying operation in terms of numbers, okay? And it's on both sides, we have the following. Okay, so this means it works as a unit. Okay, great. So that's it. That's the end of the definition. So it's a category. It's a functor like this. We call such a functor a bifunctor. It takes two elements and puts out one. It has a special element, and it satisfies these two requirements. Oh, I'm sorry. It's also true for morphisms also. For morphisms also. So F tensor G tensor H is equal to F tensor G tensor H, like that. Okay, and similar for there. Okay, great. So the rest of the section is just going through tons and tons and tons of examples. So let's do we start from the simplest example. The natural numbers, thought of as a discrete category. That means the objects are just 0, 1, 2, 3, 4, 5. The only morphisms are identities. Okay? Then the operation plus, that's going to be the operation, okay? And the unit, the thing that doesn't change anything, is 0. Okay, so that's a very nice category. And as you know from basic arithmetic, n plus m plus p is equal to n plus m plus p. All these are natural numbers. It works out very nice. N plus 0 is equal to n, which is equal to 0 plus n. Can't get any simpler than that. Okay. Great. Let's do another example. Here you have sigma is to be thought of as an alphabet. It's a bunch of letters. Okay. But you're interested in sigma star. Sigma star is a set, is the set of all words, okay? And what we're going to do is we're going to think of these words as the elements, again, of a discrete category. Okay, so we're dealing, this is a baby example, a discrete category. We could have talked about this in terms of sets, but we're not. We're talking about a discrete category. So again, the objects are strings of letters or words from this alphabet, okay? The operation is called concatenation. That means take one string, take another string, bring them together, and the unit is the empty string. The empty string is the string with no letters whatsoever, no words whatsoever. Okay, so this turns out is a strict monoidal category. Main point, concatenation is associative, and if you concatenate anything with the empty string, you get back the original thing. The original string. Okay, we're going to see later that if the alphabet is simply has a one element set, so that's a very interesting, so then sigma star is equal to 1 sigma, so that has a lot of ones. Okay, the string is basically 1, 1, 1, 1, 1, 1, many ones. Okay, by the way, concatenation. By the way, a string of length 0 is the empty string. Concatenation is simply the same thing as you have 15 ones here, you concatenate it with 12 ones here, then together you have 27 ones. Okay, so it turns out, and we're going to formalize exactly what we mean by this a little later, that these two categories, okay, this is concatenation, this is the empty set. These two categories are almost the same. The concatenation operation is almost the same as the plus operation. Again, we'll formalize that in chapter 6. Right now, we're just talking about monoidal categories. In chapter 6, we talk about morphisms between, relationships between monoidal categories. So here's a monoidal category, there's a monoidal category. Let's see what the relationship is. But I'm foreshadowing, that's for chapter 6. Okay, I just want to point out another category along this way is strings of zeros and ones. Again with concatenation, again with the empty string as that. Okay, now this is a little bit more complicated of a string, and we're going to see why later on. This is a little bit more complicated of a monoidal category, strict monoidal category. It's not the same thing as this because this has two types of things, but we'll see how that works later on. Okay, great. Both of these examples are examples of take any monoid. Again, what's a monoid? A monoid is a set with one operation and a unit. So we wrote this as follows. That's one operation and a unit like that. Well, take any monoid. So again, this is a type of algebraic structure. Take any monoid, any set with its operation on this. Well, that is a category also. Okay, and the way to do it is think of the objects of the category again as discrete categories. So the discrete categories is only identity morphisms, which makes it just a set, essentially. Okay, and you do this operation. A monoid is assumed to be associative. Okay, and this is the thing. So again, given any monoid, it forms a strict monoidal category. Okay, and this are special examples of this. Okay, great. Let me show you some more examples. You ready? Take P, a partial order. Okay, and we're going to do the following. We're going to look at the product of in a partial order. So you might have P1 and P2. It should be something like that. Same type of thing, P1 and P2. Well, then you have P1 and P2. That's the way we write the product, and this has projection morphisms. So a partial order with a product, okay, and the trivial thing is a 1, okay, which is pretty much just the product with no elements. Okay, so that's that. So this is also forms a strict monoidal category, and the idea is as follows: that P1 and P2 and P3, okay, is equal to P1, P2, P3, and like that. Okay. This is less than this. This is less than this. We're dealing with a partial order. Partial orders is anti-symmetric, so these become equal. Okay. By the way, we also have that P1 and P2 is equal to P2 and P1, which is true in here and true in here, and true when this is commutative. Okay, so that's true. That's a nice example. This is called this symbol is a product, It symbolizes the product in this thing. Again, not every partial order has a product, but when it does, we write it like this, and we call it the meet. Okay, and this is called a bounded meet semilattice. Okay, bounded because it has a 1, a meet because it's this, semilattice because it only has one operation, the AND. Okay, we'll see later what happens when we have two operations. Let me give you another example of a strict monoidal category. Okay, take a partial order, take not the product, but the coproduct. We write that as this. Okay, the coproduct of the empty set, we write that as that, 0. Okay, and so this is also a strict monoidal category because the coproduct is strict. It's also commutative. Okay, but this has a different name, bounded. Again, because this is 0. Instead of a meet, we call this operation here a join. Okay. By the way, this is just an interesting fact about category theory. You know, in a category, you can just call things a product and a thing and a join and a coproduct. Very nice. But all these things they arose in different areas. So in group theory, the product of two groups might be called the inner product. I don't know what it's called. Okay. In set, the product is called Cartesian product. We're going to see in vector spaces what it's going to be called, etc. A direct product, etc., etc. They all have different names. They all have different names because they were all developed differently. What we're showing is that all these things really have the same structure, and in a category we call them a product. But we have to learn all the names. So this is called P join 0 is called a bounded join semilattice. Okay, so it's a join semilattice. Again, the word semi, whoops, too many I's, too many M's. The word semi is because it's only half. Later on, we're going to see when they have both. And at the end of chapter 6, we're going to see a lot of these. But all of these are examples of partial orders that are strict monoidal categories. Okay, and again, this is the product, this is the coproduct. Okay, more examples. Okay. The main example, erase this and erase this. The next example and this example will be very important in the future in chapter 6. So there are two strict monoidal categories, really. This concatenation of strings, that's one thing. And here's the second one. You ready? Take a category A and look at the functors from A to A. Okay? A typical element here is a functor from A to A. Okay? Another typical element is, so we'll call that F. Okay. Another typical element will be a function, capital G. Okay, but here's the main point. We can combine these and get F compose G. So the combination is, the operation is composition. Okay, and of course, what's the identity? What's the element that doesn't change anything when you compose? Identity on A. Okay. Anyways, this is for objects. By the way, this is the first time we're having an example. I'm sorry. The partial order is also. Okay. Anyways, this is on objects. We also have to worry about morphisms. So let's do that. Okay. You might have a functor f from G, and we'll call this f prime. We'll call this G prime. We'll call this G prime. Okay. And there might be a natural transformation called alpha here, and there's a natural transformation called beta here. Okay, well, this bifunctor, it's a bifunctor, composition is now a bifunctor, okay, not only works on objects of this, by the way, we can write this as hom A, comma A, but it also works on morphisms. And so we get alpha composition, horizontal composition, beta. Okay, so we get that. Compose this with this. Okay, great. Okay, now again, just to re-emphasize, composition of functors and concatenation of strings are the paradigmatic, it's a big word, the paradigmatic, the main examples of strict monoidal categories. And when we get to chapter 6, you'll see why this is very important. Okay, some more examples. Now, the next two examples come from matrices. Okay, we're going to have two operations. I'm going to describe them here. This is called the direct product. This is called the Kronecker product of matrices. We're going to do both of these. These are two different functors that do this. But I want to foreshadow again. In next section, we're going to talk about vector spaces. Okay, and we're going to have similar operations, two different operations here in finite dimensional vector spaces. And you'll see later on how these two operations of matrices are related to the two operations of vector spaces. So let's go through it. Okay, so let's remember what K-mat is. Okay. So let's do the first example. K-mat, let's remember what it is. These are K matrices. K is a field, and the field has lots of elements, okay? And matrices are rectangular arrays, if that helps you, okay? And so let's go through the category. The objects of the category are natural numbers, okay? And a morphism from M to N is an N by M morphism, is an N by M matrix. A morphism from M to N is a matrix like that, an N by M matrix. Okay, great. Okay, so let's talk about the first strict monoidal structure of this, okay? This operation is 0. I'll show you what that means in a second. So that's an object of this category. The objects of this category are the natural numbers. The morphisms are the matrices. Okay, so first, ready? So what does plus do to the objects? M plus N equals M plus N. Can't be simpler than that. Okay, but in this category, the main thing is the morphisms, not the objects. The objects are just placeholders showing you where the morphisms come and go to. Okay, so let's do this. So if you have, in this category, if you have a morphism which consists of, we'll write this as M comma N, that's an M by N matrix, okay, and we're going to add it to, okay, now this has a name, direct sum. So that's the operation. B of M comma N prime. Okay, what this is going to do is it's going to be the following matrix: A M comma N, B M prime comma N prime. Okay, 0 and 0. Just to be formal, this is M prime comma N. This is M comma N prime. Okay, so if you have a big matrix here and you have a big matrix here, you can add them like this, okay? And basically the idea is as follows. If you have vectors here, the top vectors will be worked on right here. The bottom vectors will be worked on. The top part of the vectors will be worked on by this matrix. This will be on the bottom matrix. Okay, now I just want to be formal about what this bifunctor is. So the bifunctor is a functor that goes from, okay, for a minute, instead of talking about K matrices, we're going to talk about complex matrices, but you can do the same thing. So this goes from C of M cross N. Give me an M by N matrix. Give me another matrix, M prime by N prime. You're going to output, okay, so it takes two matrices. You're going to output a C to the M plus M prime, whoops, times N plus N prime. So you're going to, so in particular, this matrix is has N plus N prime over here, and how many columns does it have? M plus N M prime. M plus N prime. Okay, so that's formally defining what this is. By the way, the unit here is numbers, so adding 0 doesn't change anything. And what you're really doing is you're adding the 0 matrix here, and that just leaves it alone. So that doesn't change anything. So this is called the direct sum strict monoidal category on complex matrices. Let's just talk about complex matrices. Okay, these will be very important later on when we talk about quantum theory and stuff like that. Okay, but main point, this category has another, oh, I'm sorry, I left out something also. Let's just talk about associativity, namely A plus B plus C, three matrices. If you do it this way, so you're going to have a matrix, pairs of matrix, and then you're going to have a third one. Well, this is all equal to A, B, C. There's going to be zeros, matrices here. I'm leaving out the indices, okay? And this is going to be the same thing as A plus B plus C, like that. Okay, this one has it with like that, and this one has it like this, but you can leave those out. Doesn't change anything. So, conclusion, this operation is associative. Okay? Hold on. Before we get to the second thing, here's a question. We have another operation of matrices, namely regular old-fashioned matrix multiplication. So look what we have. We have matrix multiplication and direct sum of matrices. How do they get along? Okay, and the answer is, it's on page 228 of the book. I just want to copy it. I'm going to leave out subscripts. A plus B times, that's matrix multiplication, A prime, okay, plus B prime, okay, so let's write this up. This is going to equal to something like this, AB00 times A prime 0, 0, B prime. Again, in the book I have all the indices worked out perfectly, but if you multiply this out together, this is regular matrix multiplication. This is going to be A times A, so this is going to be A times A prime. That's going to be 0. 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 This is going to be B times B prime, like that, and that's equal to, so here's that matrix multiplication. So that's equal to, ready? A times A prime plus B times B prime, okay? And that's, again, that same interchange property that we had before. That interchange law, And we spoke about this a few times. We have an important categorical point. The point is as follows. You have two operations working on the same things. So they're both working on complex matrices. One operation is matrix multiplication. The other operation is direct sum. And they respect each other in this form. Okay, notice here on the outside you have two pluses and on the inside you have a times. Here you have on the outside two times, on the inside a plus. Okay, they start off both with A, they finish off both with B prime. The other twos are swapped. B, A prime, B. Okay, so finish. That's enough for one operation. The second operation is called the Kronecker product. Kronecker product. And it goes as follows. Ready? You're talking about complex matrices. Okay, a Kronecker product is written like that. And again, this category, the objects are the natural numbers, so the 1 is going to be the unit. Okay, great. Let me show you what the Kronecker product is defined as. It's a funny, it shows up all over. Okay, in physics. So let's say this is A, B, C, D. These are all complex numbers. E, F, G, H, I, J, K, L, M. This doesn't have to be complex numbers. It can be done also with any field. Okay, it's an L. Okay, great. We're going to call this A and B. So A tensor B equals, ready? A times, A scalar multiply B. B scalar multiply B. C scalar multiply B. D scalar multiply B. Okay, now that's not writing it all out. I just don't have the patience to write it all out, but let's just start it. It's going to be A times E, A times F, A times G, A times H, A times I, A times J, A times K, A times L, A times M. Okay, that's going to be one part. But besides that, you're going to have B times B, scalar multiply each one of them, C times B, and D times B. Okay, so anyways, put that all in. Okay, so you're going to have B times E, B times F, B times G, etc., etc. Nice examples in the book, very easy to do. Okay, let's just say it outside. You ready? The Kronecker product of two matrices scalar multiplies every object of the first matrix, every entry of the first matrix times the scalar multiplied times the entire second matrix. Put it all together and you get this Kronecker product of matrices. Okay. Okay. In particular, the operation goes as follows. It's much bigger than the previous one that we dealt with. This takes an M by N matrix and another M prime by N prime matrix, okay, and it outputs C, that's complex numbers, M times M prime, okay. Notice here, for every one of these guys, so you're going to have M of these, you're going to multiply it by how big this guy is. So if this is 2 and this is 3, this is going to be 2 times 3. You're going to have six columns across. Okay, cross C of N times N prime. Ah, shoot. See, N times N dot N prime. Okay, so the direct product had this with pluses over here. Now we're dealing with multiplication. So the Kronecker product is much larger than the direct product in general. Okay, great. how does this respect matrix multiplication? Okay, again, now we have three operations on matrices: regular multiplication, direct sum multiplication, and Kronecker product multiplication. Well, how does Kronecker product get along with this? And that's a line here. I just want to do it. It goes as follows. A times A prime tensor B times B prime equals, same thing. This is going to be A, this is going to be B prime, this is going to be tensor B times A prime tensor. Okay, that takes time. That takes some effort to prove. I mean, you have to just get deep down into the indices of each and every one of them, but it's important. Okay, much later on. Okay, much later on, we're going to see how the Kronecker product gets along with the direct sum. So those two have to get along also. Okay, but we'll see that a little bit later on. Okay. Okay, some more examples of strict monoidal categories. Okay, well, we started off saying like this, and I said this is a discrete category with just identity morphisms. Well, let's say I didn't want to deal with just identity morphisms. I wanted to think of this as this total order of the natural numbers. Okay, well, yes, this is also, if you think of this as the total order, this is also a strict monoidal category. But in order to do this, you have to make sure that this plus respects the morphisms too. And the idea is as follows. If x is less than or equal to y, then x plus z, that's is less than or equal to y plus c. So that works out too. Okay, great. Again, you have to just make sure that this that if there's an arrow from one to the other, then it works out nicely too. Okay, let me just give you two examples of strict monoidal categories on the total order of real numbers. Okay, one is plus with 0. Okay, so not only can you deal with the natural numbers, but it's also true for real numbers. And then there's another one which just deals with positive numbers, and take any positive numbers, multiply two positive numbers, you get a positive number, okay? And if you multiply with 1, you get like that. Okay, so here's two strict monoidal categories, okay? And in chapter 6, we're going to see how these two are related also, okay? And that's going to be something with logarithms and exponentials, but here's two nice strict monoidal categories. Very nice. Okay, next. Now, we're going to spend chapter 5, chapter 6, chapter 7 dealing with various types of monoidal categories. Okay, and this is the babiest of the babiest type of monoidal categories we're going to deal with, but obviously as we go on, we're going to get more and more sophisticated type of monoidal categories. Very nice. Okay, I want to talk about a type of strict monoidal categories that shows up, okay, namely definition, a strict monoidal category is strictly symmetric. Okay, a better name for this and strictly symmetric is commutative. But commutative has a lot of words. Strictly symmetric has there's going to be a lot of different meanings of these words. So we have to be somewhat formal with this. Is basically a strictly monoidal category, A, comma, tensor, comma, I is strictly symmetric if and only if, this is a definition, A tensor B is equal to B tensor A. Okay, and F tensor G, think of these as morphisms, is equal to G tensor F. So when you do an operation, it doesn't matter if you do it like this or you do it like this. You get the same outputs. Okay, let's just go back to here. Strings on one letter, one, with the empty string, that is a strict monoidal category. It's also strictly symmetric, because if you take a string with 25 ones and you take a string with 3 ones, you concatenate them, you get a string with 28 ones. But you can also do it this way. 3 plus 25 is equal to 28. So that works out too. However, this, with 0 and 1, if you have an alphabet with 2 objects, any 2 objects, doesn't have to be 0, 1, and again you're talking about concatenation, and again you're talking about an empty category, then it's not strictly symmetric. It's not commutative. The idea is as follows. You take a string of 0s and 1s, you take another string of 0s and 1s. In general, if you concatenate them this way, it's not the same thing as if you concatenate them that way. So it's not strictly commutative. Okay, great. Let's just talk about this operation of matrices and this operation of matrices. In general, they are not strictly symmetric. Okay, they are not strictly symmetric, and that goes with all the operations on matrices. They're usually not commutative, which makes things a lot more interesting. Okay, one more theorem, and we'll call it a day. Okay, and this is called the Eckmann. This is an old Hilton argument. This is an old topology result, but we can talk about it in terms of categories. Okay, it's the same type of structure as before. It goes as follows. Take a monoid, thought of as a one-object category. Okay, so let's just think of it as you have one object, and all the morphisms of M, all the objects of M become morphisms from that one object to itself, and you have concatenation. Okay, right, you compose the morphisms, and that's the operation over there. Okay, now take this, it's a category. Now let's say you also have, on this category, you have a strict monoidal category structure. So not only does it have this operation, but also I'm going to make this operation on it. I'm sorry, this structure on it. So again, this is a category thought of as a one-object category where the morphisms are this. This is a category thought of again as a one-object category, but now it has this other operation too, which operates on it. So composition of the monoid is one operation. Concatenation, I'm sorry, the monoid operation is another operation. Okay, so answer. When you have these two structures on the same set, what you have is the following. First of all, the two operations coincide. The two operations coincide. Second of all, the two units also coincide. as before. And this is, I go through the proof in the book. It's a half a page. It's exact, whatever. It's a nice proof, but it follows just from the definition of what it means for this to be a monoidal category. They have to satisfy this requirement. This has to be a bifunctor. This has to be a unit. This is satisfied. But something else, okay? And this is not seen before. A times B, which is equal to A plus B, which is equal to, because these two operations are the same, is going to equal to B plus box A. Okay, that's a shocking thing. Okay, it's commutative. It's commutative. I never said a word about commutativity here, strictly symmetric. I never said a word about here, commutativity or strictly symmetric, but because these two monoids have two operations and they satisfy the requirements of respecting each other, then it's commutative, which means also that this operation commutes. So this is equal to this is equal to this, they're all equal to each other. Okay, so, but this is something a little bit different than we've seen before. Namely, the idea is as follows. When you have one operation, that's fine. It could be commutative, it could not be commutative. But even if it's not commutative, if you add a second operation, then that second operation is going to force the first operation to be commutative. Okay, and again, it's an old topology result, but it shows up. However, we're going to see later on, we're going to see higher dimensional versions of this, where you bring in more operations, makes the operation that you have be stricter in some sense, satisfy more axioms. So we're going to see this much later on in chapter 9, chapter 9, chapter 10 a little bit, how these extra higher dimensional operations cause this to be done. Okay, so recap, strict monoidal categories are categories where you can combine elements and everything works out very, very nice. Next section, 5.2, we talk about Cartesian products, where things don't work out as nicely, but we'll see. Take care.